Henry Hickman. I'm a new lecturer here, and Jake is a bit busy today because he's a bit busy being in Italy, so he can't give the lecture right now because currently it's 9 p.m. in Italy, and also he's probably having a lot of cured meats and pizza. But we do have me, and before we have me, we have someone from DevSoc here to talk about the very cool things that they're doing. You have 5 minutes.
Wait, hello? Hello. Okay, I'll just yell then. Okay, hello everyone. Hello, lecture recording. I hope you guys watch this before in time, before the event's over, but we'll see how we go. I'm just here today to talk about DevSoc's project showcase they have going on. Basically, it's just a week again, but very specifically for software like CSC and mechatronics over there. So what we have like 35 amazing projects. We kind of lay them out kind of similar to a week. Each thing has a stall, like 1, 2, 3, 4. We get the societies in there. So this is like Redback with a car as well, and they have some other independent projects as well. So the idea is that you can walk around, chat with the devs, kind of figure out what things you like, what things you might not like, what opportunities you might want to join, like as a subcom next year in one of these larger teams as well. So yeah, just an example of what we have on display. We have like a note-taking app. This is an app that does OCR to steal a Pokemon Showdown team from a YouTube video. It's very random. A few more personal projects like portfolio type stuff. Maybe game. We have a mobile app that locks your phone down so you can lock in. Yeah. Next up we have our societies. So we have BlueSat. They make the rovers and the ground station. They actually send stuff into space, and that's how they talk to it. We also have Crate that has things like the Spiderbot. Oh, shoot.
It's okay.
Anyway, yeah. If you're more interested in the mechatronics side and working on more embedded systems, we have like RamSoc Sumo bots coming along, Redback's car as well, and it gets a bit more silly from here as well. So here's just like a lane detection car. You can see some of the pseudocode that they've written down below. We also have some vertically integrated projects, such as the underwater UAV. This is the swim team. I believe they won some competition in Singapore recently. That'll be cool to check out. If you're interested in the AI stuff, there's some people that have taken a shot at a few things. So on the left here, it's like lecture notes into frame rot videos. I'm not sure about, I'm interested about that myself. I'm gonna check that out another day. And there are a few other things around the place as well, if you're interested in that. Finally, we have some security and low-level stuff. So we have someone from, I think it's 684 Tutor, that's made a like a cybersecurity education website. So this is like a phishing mini game where you can click on what's suspicious in the email. We also have someone from the operating systems Cell 4 team that's doing a thesis with them at the moment. So you can talk to them more about if you want to do low-level operating systems research. Finally, we have some other DevSoc related things. We have an AGM voting system in the works, your guests on campus, and a lot of projects, free rooms, and our timetable planner. Yeah, so apart from that, have a look around, see what you like. At the end, we have a bit of a fun Q&A panel where you just like ask whatever to the project presenters. It's normally quite casual. After that, we have our industry guests come up on that panel. You get to ask them a few questions. We have everything from a like very large and established, like IMC, down to like something towards the middle, safety culture, and then startups with Lyra at the end. So for anything you might be interested in, there's probably something for you here. As for societies, we have these 6 coming along, and we're also supported by the School of Computer Science and Engineering. So thank you. You can win a bucket hat. Apart from that, thank you. I hope I see you guys there. Yeah, come see what you're interested in, and also discover the free food. We have lots of free food. It's Friday, 4 p.m. at the Roundhouse, and more information is on our website. Right. Thank you. I'll hand it back over to Henry.
Nice, thank you. As someone who plays far too much Pokemon Showdown, you're speaking my language. Big fan. Right, I've also been told to plug a few things before the lecture, so we will get into linked lists very shortly, but first, is everyone aware that assignment 2 has been released? Is anyone like not aware of that? All right, well, assignment 2 has been released. You can find details about it somewhere on the website, I assume. So you should really do assignment 2, and it's all about linked lists. So you should also really lock in for these few lectures because they will help with assignment 2 quite a bit. There are also some help sessions. I was specifically told to plug the week 8 help sessions. Is there anything special about the week 8 help sessions that require me to plug it? Just that it does exist. Yep. So if you are struggling and you need help, there are help sessions. They will help you. That's sort of why they're called help sessions. And so I highly encourage going along to those. Linked lists are difficult. Linked lists can be challenging. You may need to rewatch the lectures a few times. And so I do highly recommend, if you are struggling, go to the help session, get some help, and it will make your life a whole lot easier. Now we are on to linked list part 2. Before we dive into it, I will just say a little bit about me. I'm from this small country. You may not have heard of it. It's called New Zealand. Is anyone familiar?
I know New Zealand.
You know it?
Yep. I've moved there, actually.
Nice.
Yep.
I also used to live there. I don't anymore. That's why I'm
yes.
here. My life.
Oh, really?
Yeah. And in New Zealand, when we teach introductory programming, we teach in this language called Python. And this means that sometimes when I write some C code, I will forget my semicolons. I'll write print instead of printf. And instead of trying to make that really annoying for you, I'm going to try and make that more fun. So if you see me do something like that, yell at me, and one of the tutors will throw chocolate at you. I've got some caramello koalas and Freddo frogs and whatnot. So just if I accidentally write Python code instead of C code, point out my mistakes. This is a form of peer learning in of itself because identifying and teaching others and telling me what I'm doing wrong improves your programming. And so we should all work together to make this lecture a bit more smooth. Cool, sounds good. Linked list part 2. So last week, Jake went over introducing the concept, and it says that he went over inserting at the head, but I watched the lecture. He didn't. So we will go over inserting at the head today. He also went over linked list traversal in sort of a roundabout way. He went over how to print all the items in a linked list, which is a form of linked list traversal. There's a few different ways that we'll only traverse it one way in this course, but there are a few different times we'll need to traverse a linked list. It happens all the time. It also says that he went over insert at tail. Again, I watched the lecture. No, he didn't. And so we'll also go over inserting at the tail today. And if we have time, the lucky thing about this last topic is that we do have a few sort of buffer lectures. So anything, I'm going to fit what I can at a speed that I feel is appropriate. Please do yell at me if you think it's too fast or too slow. But anything that I don't cover today, Sophia can cover tomorrow in the online lecture. And if anything Sophia doesn't cover tomorrow, I can then cover on Monday next week. So we have plenty of time to get all of these concepts down, and it will be very useful to get them all down for assignment purposes and for exam purposes and for being just like better programmers when it comes to linked lists. Cool, so who here is comfortable with this idea that a node is a struct and a linked list is just a chain of nodes? Were people happy with what this means? What does it mean when it says that it contains a pointer to another node? Why do we do that? Yeah, to link them all together. That's why it's called a linked list. Well, how is it different from just a regular array? Yeah, yep, you can throw chocolate at them. I don't know, they're deciding when they throw chocolate at you. How's a linked list different from a regular array? Yeah. It's not contiguous. Yep, so an array is contiguous memory, one after the other. All of your elements are sort of in a row. Well done. And a linked list, your bits of memory can basically be anywhere on the heap, and we just point between them. And so your struct is a node. It contains a payload, which we're going to deal with integers right now, but you may deal with other types of data later, and a pointer to another node. So it looks like this in code. You've got your struct nodes, you've got your int, your data, which is your payload, and that points to another node. And so if we look at linked lists, if we visualize them, I'm going to go over to the whiteboard. Just like what they say here, we have our node, which contains our data, which might be the number 4. And then it also points to our next node, which contains some data. It might be 7, and then it also points somewhere else to our next node, which may contain some data of some sort. What's your favorite number? All right, good answer, 15. And how do I know when my linked list has no more nodes for me to point to? What am I going to point to instead? Null? Yep. So at some point, my node will point somewhere, and it will be null. And I have to allocate memory for each of these nodes in the linked list. And I need to figure out, once I've allocated the memory, I also need to start there somehow. So what do we have that lets us start traversing our linked list? We actually have another pointer. We have our starting pointer, normally referred to as head. And that just says, this is the place in memory where our linked list begins. And so head points to the start of our linked list, each node points to the next node, and eventually it points to null, which means you're at the end of the linked list. So when we are creating a linked list, we define the struct. Yeah, we have the pointer to keep track of it. And what we also need to create a linked list is a way to create a node and then connect it into our list. And that's what we're going to cover now, I reckon. Yeah, who wants a demo, or who's happy with my ramblings? Yeah, demo sounds good to me as well, because code is good. I don't really want to ask Copilot things. Don't really want that there either. Is this big enough? Oh, that's probably too big. Is that big enough? People feeling smaller, bigger, just right? How's it look on the stream? All right, I'll take your stunned silence as it's good enough. Cool. Right, so we have our node, which contains the data and contains a pointer to the next node. These structs are the basis, the foundation of all of our linked lists, and so it is good to be working with them and to understand what they mean. Jake made a function for creating a node. It mallocs the size of a node, which means it allocates enough memory for us to create that node. It puts the data that we want into the data part of our struct, and it sets the next node to null. So when we create the nodes, we're not linking them to anything. We're just creating places in memory where nodes exist. They are not linked up yet. When we talked about traversing the linked list, this is the printing linked list. That's a form of traversal, because we start at the head and we say, right, we are here. Is our next node null? No. Actually, we don't even say that. We say, is our current node null? That's a spoiler for later on. Is our current node null? It's not, so we can print 4. And because our current node is not null, we'll move on to the next item in our linked list. Is this one null? Is this null? No. Nope, it's 7. And so we can move on to the next node in our linked list. Is this one null? Nope, still not null. It's 15. So we move on to the next node in our linked list. Is this one null? Yep, it is. And so we have traversed our linked list and printed each element one after the other. So that is a form of linked list traversal, to print the elements in a list. And then what Jake did at the end is that he created 3 nodes. He created one called head. Well, it's a pointer to a node called head, and another one called second node and third node. He said that head's next element was the second, and the second's next element was third. And so if I, oh cool, caps lock, thank you. DCC, linklist.c. And if I run that, he's allocated 16 bytes per node, and at the end of it we get a linked list which goes 11, 8, 7, and then null. So that's printing the linked list. That's what we've done so far. But there is something that Jake's forgotten to do, and it's a terrible thing, and it's awful, and we should never forget to do this. What should we never forget to do ever under any circumstances or else? Free the memory. Yep, yep. All right, I had a whole metaphor for this, but I don't need it anymore. You guys all know if you allocate some memory, you must free it. I'm going to use the metaphor anyway. I spent way too long thinking about it. To me, I view the heap almost like, who here has a pet? Yeah, some people have pets. And I see the stack as like when you live at home as a kid and you have a dog, you just get to have fun. There's no sort of responsibility there. You get to play with the dog, and then when you're done with that, your parents look after it. But we can't do that anymore when we're on the heap. We need to look after every single thing. Every time we malloc, we have to remember to free it. Just like when you get a dog of your own when you're an adult, you have to look after every single part of it. You can't just have the fun anymore, you have the responsibility that goes along with it. That's my metaphor that I genuinely spent a disgusting amount of time thinking of. I hope it was worth it. Thank you, I will take stunned silence or applause. Oh, it's so easy, it's so easy. Right, so let's free our nodes in the linked list. What am I going to have to pass in to actually access the linked list? Yep, so the type that I'll pass in is a struct. In fact, it's a pointer to a struct, but what is where does our linked list start? It starts at the head. Yes, good stuff. So I'm just going to write, we're going to free all nodes in the linked list. This is a part where it will get pointers. You're going to want to use the scrap paper in the exams, is essentially what I'm saying here, because trying to keep track of pointers in your head is hard. I've been teaching linked lists for several years now, and still sometimes you just want a bit of paper to write it all out on. But we'll see how far I can get without it, because I love showing off. And if I make a mistake, it's funnier that way. So, one thing that's good to always do when you're dealing with a linked list is that you should make a node, a pointer called current, and set that equal to your head. And so this means we're not going to change the head. We have a different node, a different pointer that we can update now. It points to the same node that head points to, but now when we make changes like going to the next one, we've not changed the head anymore. How many of our nodes do we want to free? How many of our nodes have memory allocated to them? Right, 3 is the right answer, but in terms of like a general linked list, how many of them? All of them? Yes, every single node will have had some memory allocated to it, so we'll need to free every single node. So how do I go through, how do I traverse my list and visit every single node? Yep, a loop. Yep, I'll use a while loop, I think. And it's what we talked about before. We'll go while current does not equal null. Yep. And we won't worry about freeing just yet, but let's just do the part where we go current equals current next. And then, yes, so what this will do is this will go through every single element, one after the other. We make our pointer called current, pointed at the same place that head points at. We'll look at it real good, and then later on, once we're done looking at it, we'll move the pointer to point at the next one. And then once we're done looking there, we'll point at the next one. And once we're done looking there, we'll point at null. As you can see, I'm an artist. Terrible whiteboarding. So that's us traversing the list. But what we need to do is we need to free things. What's going to happen if I just free current? Yes, I can't go to the next one if I free current. So I'm going to do the same thing we just did, where I'm going to go similar to when I make current so that I can point, so I can look at where head's looking at. I'm going to make a node called node to free and set it equal to current. All right, that's me being Pythonic. I need to define my types. Right. And now current is the next one, so what should I free now? I've given you a hint in the name. Should I free current? I should free the node to free. And so what this will do, it goes through each node and it frees it. Oh man, okay, give him chocolate. Thank you. And so at the end of my program, I'll call my free all nodes function. Is that what I called it? Yep, I called it free all nodes. And I'll pass in the head. And that ensures that we don't have any memory leaks. Like for a small program like this, the memory leak is probably not going to matter because the program does terminate. But for if you were writing, as Jake said in the lecture, just a simple app like Instagram, then it's going to be a problem because that will never close and the memory leak will get worse and worse and worse. No. Same thing happened last lecture. No. And I'll put a print statement at the bottom so that we know that we've freed all the nodes in the linked list. Hopefully now. Oh man, another. Thank you. I'm hoping that through this sort of public ridicule, I will become a better programmer.
Do you need a return?
So why do I not need a return? Can someone? It's a void function, which means it doesn't return anything. But good question. So I will compile my code. I will run it. And we've now freed all of the nodes. There are no more memory leaks. And we are happier people. Are we happier people now? Do we feel happier? Yeah, I feel happier. Awesome. I will say Jake did specifically say to me it's very important to go over this because the most common place where people lose marks in assignment 2 is not freeing the things that they malloc. So please, if you malloc something, free it. Hello.
Do you want to run it with DCC leak check, and then you can show that there are no errors that come up when you free it, and then without.
Sure. Now, here's a question. How do I DCC leak check?
DCC.
Yep.
And then just before the linked.c.
Yep.
2 hyphens. Leak. Hyphen check. Yep, and that's it.
Cool. Yep, no errors. And if I comment out this part where I free all of my nodes, hopefully if DCC is as cool as I've been told it is, I will be told that I have some errors here. Or some leaked memory. I've not.
You get the error when you run the program.
I get the error when I run the program. Yep, so free's not been called, even though I've malloc some memory. And if I go back to freeing all of my memory, there are no errors. So we can see the difference. There are errors and there are not errors now. And generally when we're programming, we're a fan of not having errors. Is that a statement that we all agree with? Yeah? Nice. Cool. All right, what is next? All right, so going back to the things that Jake claimed to have done but didn't actually do, we now need to figure out how to insert things into our linked list. We will want to insert at the head, which is at the front, or an insert at the tail, which is the name for not the front. It's the end of the linked list. So head is the front, tail is the end. Let's demo those. Or in fact, let's whiteboard about them, shall we? All right, not as enthusiastic as I expected for the concept of whiteboard, but fair enough, we'll get there. So let's say I have a linked list. And then maybe it comes down here as well. And then it points to null. and I want to insert something at the head. So the first thing I'm going to do is I'm going to create another node, and it's just going to sort of sit on the heap in the memory somewhere. So I've got my node, it's going to have the number 15 in it, and it's just sort of there. How can I draw the arrows to link them up? What's the order that I need to do things in? So the first thing that I'm going to want to do is I'm going to want to take this node and say that its next is what the head currently is, because that's going to put it in front of the head, right? So if I take this node and I say your next is the head, that's going to put it at the front, right? But the problem is, how do I get to it? Because we can't go backwards and the head still points here. So what do I need to do to the head to make this work? Yep. Well, I don't need to reassign the heads next, but I need to reassign head. What does head point to? I need to reassign head. Yes, to go over here now. And now I've inserted something at the head of my linked list. All right, that's a sort of whiteboard discussion. Are there any questions about the sort of theory behind what we're doing here? We're taking a node, we're putting it in front, we're saying that the next item that comes after our new node is the old front of our list, and now it's the front of our list. Let's try programming some stuff. If I were a better programmer, I would break this into a bunch of files, but for the purpose of this lecture, I'm not going to do that. So we're going to make a function that returns a node, and it's pointed to a node, and it's going to be called insert at head, and it's going to take a node, it's going to take the head. Actually, it's going to take the head, and what else is it going to take? Yep, the thing I'm inserting, which is going to be called, I just call it a new node for essentially everything. And it's going to insert at the beginning of a linked list. Pretty much every time I write a linked list function, I like to do this. I like to go struct node star current equals head. And so what we're going to do now is we actually don't need a while loop. We don't need to traverse very far because we're at the head already, right? So what I'm going to do is I'm going to say that new nodes next node, what's this going to be equal to? We've got the front of our list called head. We want to put something in front of it. So what's the item that comes after our new node?
The previous head.
Yep, the previous head. So in fact, that's a much better name than current. I'm going to call this previous head, or prev head for short. Sorry, sorry, say that again, I can't hear. On line 62, it should be prev head now. No, it should be, yeah, it should be new node. I've got the semicolon. I think this is fine. I think this is fine. I'm doubting myself, but I'm pretty sure. Is it fine? It's fine.
Yes, it's fine.
Yeah, I believe. And I was going to say that the head is now equal to the new node, and I'm going to return the head. And that is how you insert something at the head of a linked list. But what I'm going to do is I'm going to put my money where my mouth is and try running it. So Jake's got these lovely nodes that he's made for us, but I don't want them to be done like this. So actually what we're going to do is we're going to call our function. I'm going to say head equals insert at head. It's going to take the head, going to take the second node, And I'm going to do it again. And the third node. And so if this works how I want it to work, what we should get is a list containing 7, then 8, then 11. Because I've put the head, and then I've put the second node, which contains 7 in front of the head, no, 8 in front of the head, and then the 7 in front of that. So let's see. Yes, cool. So we started with, let's walk through it on the whiteboard again. I almost drew on the wall, that would have been poor. So we started with our original node. It contains 11. It points to null. And head points to it. Then we made a new node. It contains 7, and it points to nothing right now. What we did is we said that its next node should be what our old head was. And then we said, and what our head points to should no longer be what the old head was. It should actually be our new head here. Then we created another node. It had an 8 in it. And we said this node should point to our current head. So we pointed it this way. And then we said, actually, our head should no longer point to what's second in our list. It should instead point to what the new start of our list is. And this can continue going as many times as we want with inserting things at the head of our linked list. People might be wondering why I have to return head, because I've made a function that inserts at the head and returns what the new head is. There are some edge cases with linked lists that you should probably always be thinking about. For example, what happens if there is no items in the linked list? Does my code work for that? No, my code does not work if there are no items in the linked list, because if the head is null, actually it might. I'll leave that as an exercise for the reader. I don't think it does, but it might. No, I should be able to logic through this. If the head is null. Huh. All right, let's walk through what happens if the head is null. What was that? Yeah, they should. Yep. I've done them in the wrong order. So if head starts as null, and we have some node here with a 5, I say that the node is the previous head. Yep. And I say that the next node from this node is whatever the previous head was. So actually, in this case, there's no reason that the head has to not be null, but there are some cases where the head being null will blow your legs off. So keep it in mind. Keep it in mind, especially when you're doing assignments. Edge cases like that are always things that assessors love to include. Right, so we've figured out how to insert things at the head of a linked list. What time are we at? What about inserting things at the tail of a linked list? Who thinks that's going to be just as easy? Who thinks it's going to be marginally more complex? Yeah. Why is it going to be more complex? Why can't I just say, I'm just going to put it at the end? What is it about linked lists that make inserting things at the tail a bit more complex? I have to go through every single element first. Perfect. Right, so let's make our function that will do that. Struct node star insert at tail, and again it's going to take the head pointer and the new node. We won't worry about the case of the head is null right now, but that is one where we would have things go awry. I'm going to say struct current equals head. And now let's just do while, we're familiar with this pattern right now. What's the pattern that we've been using every time I wanted to traverse the linked list? Yeah, while current does not equal null. And I'm going to say current equals current next. And now to the whiteboard to explain that I've tricked you. You've fallen for my trap, and I'm sorry about that. So let's think about where we're going to end up with our linked list here. So current points out what the head is. And remember, our goal at the end of all of this is this node over here that I'm going to make should be pointed to by this node. So, is current null? Nope. So I'm going to go to the next one. Is current null? Nope. So I'm going to go to the next one. Is current null? No. So I'm going to go to the next one. Is current null? Yep. So I've stopped here. Now how can I link it up? I've overshot. I can't link it up to with the previous node because you can't go backwards in these sorts of linked lists because we have a singly linked list. We're moving forward at all times. So actually, I need to stop here. Because once I stop here, then I can reassign this to point to here. Does that make sense?
Can you just change null to something else?
You can't just change null to something else. Can you elaborate on that one? Because I don't know enough about C. And I know you can't do it, but is there like a more in-depth explanation students would require? Null is a special bit of memory. You can't do things to it.
It's like the zero value for pointers.
Yeah, he said it's like the zero value for pointers and we can't edit it.
Why can't you make it a struct?
Yep.
With the non-terminating character and a pointer at the bottom, something like this.
So the main problem we're facing when we get here is that we can't go backwards. So there's no, this part, even if this was a pointer, it doesn't actually know what came before it. So we can't look at previous. And what we need to do is look at what came before us and assign that to the next one.
Well, you can make it a struct without a pointer, just a struct of non-terminating character and just nothing. Does that work?
I could put a struct there probably, but it wouldn't link it up because it would be put in a different place in memory when we did the malloc-in. Yeah, does that sort of make sense? Cool. All right, so if we don't want to stop when current is null, when do we want to stop? When current next is null. So while current next is not null, we're going to move down, and so this time, back over here, oh, I need to redo my arrows. I'm getting, oh no, my whiteboard marker's fallen. Right. Is current next null? No. Is current next null? Nope. Is current next null? Yes. Current next null. Current next is null now, and therefore we stop and we add our node at the tail. So we've stopped, and now what I'm going to say is current next is equal to our new node. And I'm still going to return the head because there are some cases where we would change head. And I believe now, if I change this from insert at head to insert at tail, in fact, I might make a few more nodes. So let's make some more nodes. Struct, node star, fourth node, And I'll create a node with 15 in it. This naming convention for the nodes is awful, by the way, because, well, it is good if I know for a fact these are going to be the second, third, fourth, and fifth node. But with how I'm going to do this lecture, they're definitely not going to be all the time. It's already out of order now. I'll create another node, and this one will have 20 in it. So let's see if this works. So now I have a list containing 11, 8, 7, 15, and 20. They've all been inserted at the tail, one after the other. Do we have any questions about inserting at the head or inserting at the tail so far? I'm going to go through and redocument the code because I realized my level of documentation compared to Jake's is currently a bit lacking. Have I flipped it? I've inserted everything at the tail, and so our first node is 11, and then our second one is 8, which I... no, I believe they're in the order that I expect them to be. 11...
Like 7, 8, 11 before.
Yeah, yes. Sorry, yes, you're right. So before I was inserting at the head, so I was putting them at the front, but now I've flipped it and I've inserted them all at the tail. Yeah, so I have reversed the order from before. Yeah, correct. Cool. So let's go through and do some oh my gosh. Why did I not document my code at all? That's terrible. This is awful, awful behavior, Henry. So this is a function that inserts at the tail of a linked list. This while loop is so that we don't fall off the end of our linked list. Stop when the next item is null. And then down here, we are at the very last node in our list. Make it point to our new node. And our new node already points to null, so we don't need to worry about that. And then inserting at the head. Our new node points to what used to be the start of the linked list. The start of our linked list is now the new node. Cool. Are there any questions online or in person? Anything on the stream? Anything on the IRL lecture theatre? Hello.
Sorry, question. I was just going to ask, would you mind popping the function comments just above the definition?
Yep. Yeah. Funnily enough, you get chocolate because in Python, doc strings go under the function definition, but in C, they don't. And I didn't know that until right now. So good job. Are there any others that I did? I should document the free in all nodes as well. So this traverses the linked list until we're at the end. And this one says, gets the current node in preparation of freeing it. This one moves on with our life to the next node. And this frees the node so we don't lose marks in the assignment, have a memory leak. Right, and so now, with all of that, we've caught up to where Jake wanted us to begin this lecture. And it's only taken us half of the lecture. This is a good pace. Yes. Right, so anyway, that's all the stuff we've already done. Let's talk about what we're going to do today. So, what we're going to do today is we're going to insert at an index, we're going to delete a node at an index, we're going to remove the tail, which is just deleting at the last position, and we're going to do the size of a linked list. We're probably not going to do all of these, and in fact the slides don't even recommend that we do all of these. So let's start with inserting in the middle of a linked list, or particularly at an index. We have had inserting at the beginning, we've inserted at the tail, and so now how do I insert just generally? What do we need to worry about now? If I want to insert a node between 8 and 11, I need to worry about a few things now. What do I need to worry about?
There's 2 8s before.
Yep, there's 2 arrows, as it were. So if I put the 10 here, what arrows, what pointers do I need to worry about? What does the 10 need to point to?
8.
Yep, 10 needs to point to the 11. But then what else do I need to change? The 8 needs to point to 10. So we need to update 2 pointers to be able to insert in the middle. But actually, I've just realized there's one thing about inserting at the tail that I've not covered that's relatively important and you may want to think about. Inserting at the head should work even if the head doesn't exist. Will inserting at the tail work if the head is null? Yeah, if the head is null, inserting at the tail won't work. Because if the head is null here, the very first thing that I say, or I suppose the second thing that I say, is I try to figure out what the next node after the head is. What's the next node after the head here? It doesn't exist. C is going to be very mad at me if I do that. And so we need to think about what we can do if the head is null. Because what's inserting at the tail of an empty linked list? If a linked list is empty, it's just making the head, it's just inserting at the head. So there are a few ways we could go about doing this. What I'm going to do is I'm going to say if the head is equal to null, it's going to be, actually no, if head is null, I'll just go head equals new node, and I will return head. And we're done. So let's try this now. A bit of a trick, I'm going to make a new linked list by setting my head to be equal to when I insert at the tail with null and the 5th node. So I'm making a linked list where the head is null and the first element is the 5th node. So what should get printed out here? The 5th node contains 20, so it should just be the number 20, I think. Nope. Done something wrong there. I've not saved it. In Python, it saves for you. Error. Free not called. Oh yes, so the reason the error is, well, why am I getting my free not called error? So my free function is actually in the main function down here, but the reason it's not been called is because all of these nodes here that used to be part of a linked list have just gone ignored. I've just gotten rid of them. I've just said, actually, I'm going to make a new linked list with the head over here. And so what I should do instead is I should actually probably just call this head 2. And then at the end, I should call another free all nodes and call it starting at head 2. man, what have I done? Hey, can anyone tell me what I've done wrong here on line 105? I have to declare the type because this is C and not Python. Nice. Still not printing what I wanted though. Oh yeah, because I've called print on head instead of head 2. So now let's call print linked list head 2. And there we go, we've got 2 linked lists, and one of them that I created by just having head as the null and inserting a node into it. All right, now we can get back to inserting anywhere in the linked list. How do we sort of label positions in an array? What are they labeled as? Yeah, integers. And what do these integers sort of refer to? There's a special word for them, probably doesn't really matter, but yeah, index. And so I'm going to say that linked lists can also have an index, we just can't index into a linked list. So I know that is everyone here happy if I 0 index my linked lists? So the first element is element 0, and so on and so forth. Cool. Just have to make sure we're all on the same page with that. We'll go insert in middle. We'll take a head, and we'll take a new node. Middle of a linked list. In fact, it's probably going to take a third argument because we need to know what index we're going to insert at. So let's also make an int called index, which is where we're going to insert. Right, so let's say that, let's start with our classic struct node star current is equal to the head. But I'm going to make another variable called counter. And what do you think count is going to do? It's going to count, but what are we counting up to? Yep, we're going to try and get up to the index. So instead of our while loop being while current is not null or while current next is not null, what should our while loop be instead? Nice. So we're going to go while counter is less than index. There's a small trick here with inserting into any sort of data type. If I want to insert, let's say like in this scenario, I want 10 to end up at index 2. So I want it to end up here where it will be index 2. Which means I actually need to stop here. And which index is this?
1.
This is index 1, this is index 0. I want my node to end up at index 2, so I need to stop at index 1. Because if I stop at what is currently index 2, then my node will become index 3. So we need to stop 1 earlier. So what should my while loop be? Yep, index minus 1. One of the tutors, could you please quickly check if the Kahoot requires deleting? Do you have the ability to check that? All right, fine. We'll just wing it. We're going to go current equals current next. So we're going to go down the linked list. We're going to go to the next element, and we're going to go index. No, not index. We're going to go counter plus plus. So now we've ended up here. We've ended up where we want to be. We're at index 1, we want to put our 10 in, and we've got the item after. This is where the whiteboarding and the pen and paper comes in really handy because we're keeping track of a lot of stuff going on here. So as a recap, our list will currently look something like the 8 is pointing to the 11, new node is chilling, and current points to here. So, where do we want to start? What do we want first? We want 8 to point to 10. Okay, let's say that I start with 8 pointing to 10. Now, how do I get 10 to point to 11? It's gone. It's been lost to the ether, as it were, because there's no more pointer to 11. So I can't get there anymore. It's gone. So we can't just make 8 point to 10 immediately. Yep, we can make 10 point to 11 first, because then there's 2 things pointing to 11. And now that 10 points to 11, I can make 8 point to 10, because now 11 won't get lost in that ether. Does that make sense? Before now, if we point 8 to 10 first, we're just going to lose 11 entirely. But with this, we can not do that. There are a few ways to go about doing this, and I'm going to do the slightly nicer one because the other one's not that nice. So I'm just going to make a node called, I'll call it old next, and I'll set that equal to current next. So this is what currently points at. Yep. So this in this scenario, that would be the 11. That's what current is currently pointing towards. Now, I'm going to say that current's new next. So what do we want current to point to now?
10.
Yep, which is more generally our new node. And now, what do we want our new node to point to? Old next. Yep. So there's a bit of a dance that goes along here to get this working, but this is the order in which you should do the operations, and then things can't go super horribly wrong, I hope.
Do you have to do anything with index?
No, index served the purpose of getting us to where we wanted to be inserting. So index's goal was to serve as telling us where to stop.
I don't have to like declare it or anything.
It's declared in the function definition up the top.
How does that work?
So when we want to insert in the middle, so let's make another node. I'll make this just the regular head again, and I'll get rid of these lines about head 2. So right now, oh man. Oh right, I don't need to do that. Head. So right now we have a linked list containing, I'll put it up on the board, it goes our linked list goes 11. What does 11 point to? 8, thank you. And what does 8 point to? 7. And what does 7 point to? 15. And what does 15 point to? 20. And 20 points to null. And the index of each of these elements is, this is the first one, so this is 0, 1, 2, 3, 4. And so when I call my insert in middle function, I'm going to say, first I'm going to create a node. I'll go struct node star 6th node equals create node, and I'll make 55. And I'm going to call head equals insert what do I call the function? Insert in middle. It should really be called insert at index because the index could be 0, the index could be the last item, so I'm going to change that to be insert at index. Always make sure your function names are descriptive and actually match what you're doing, otherwise people who work on your code later will be very sad. Insert at index, so we'll take the head, we'll take our new node called 6node, and then you were asking how index works. We just decide which one do I want to insert it at. So pick a number from preferably 1, 2, or 3. 2. So I can just put the number 2 here, and so when this code runs, the number 2 will get passed up. Thank you. The number 2 will get passed up into this function, and the index here will be 2. Cool?
Yes.
Sweet. So hopefully we will end up with a linked list of 11, 8, 55, and then the rest. Drat. Thank you. I didn't save it. I'm a good programmer. I'm just bad at saving things. Yes, good. We've done it. Thank you for the emotional support. Right, it's currently 10 past 12. So we can either look at deleting, or we can take a break, do the Kahoot with the caveat that there might be some deletion stuff in there, but it's just a Kahoot. Who wants to take a break? Okay, lots of hands for break. I'm not counting it, but it seems like a quick 10-minute break. Is it normally a 10-minute break? 5 to 10 minutes. Take your break, get ready to Kahoot, and then come back ready to roll. All right. See you in I'll say 5 minutes because we've got Right, we're at 46 so far. Can we hit 47? We've hit 50. We've hit 50. Can we hit 53? Oh, we've hit 53. Can we hit 57? Oh, we're smashing it. All right. Put your hand up if you're not back yet. All right, cool. Sweet. Are people online ready to roll? Yep. All right, cool. Hi, I've just put the mic back on. Can people still hear me? Hello? Hello? It's the Pikmin noise. Cool. Right. Is anyone not back? Yeah, it's probably fine. Let's start. This is a Kahoot all about linked lists, I think. I prepped for a different Kahoot, and so I will be playing alongside you. Here we go. Which of the following correctly mallocs a new node? Great question. Yeah, sorry, we need to do the music. Dun 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 dun. Right, so right I know it's exciting, but let's calm down. To malloc a new node, you must say that you're making a pointer to a node because malloc gives you a memory address, and you need to malloc the size of the node itself. So yellow. Lots of people put blue. The people who put blue, yeah, blue has a pointer at the end, and we're not mallocing the size of. Yeah. Yeah. Cool. All right. On to the next one. Yeah, and so blue we're mallocing a pointer, which will not be enough space. Probably won't be enough space. I'm not going to confirm that. All right, smart dog living up to their name. But is anyone here up dog?
What's up, dog?
Oh, nothing much. What's up with you? How would I, me personally, set the data in my node type struct node star named new node to 99? So yes, it is new node pointing to data is equal to 99. I feel like the time limit on this is a bit short. Okay, sorry, I'd like to say I didn't write the Kahoot, but the time limit on that one was a bit short. But when you have a node and you want to set its data to be 99, you use the little arrow to dereference it and set its data to 99. Hello. Yeah, but I saw one of them was mean, and I don't. This is close. If this was new node, it would be new node pointing to data. All right. Nothing's changed. Right. I have a node current, and I wanted to point to the next node. What have I been writing repeatedly? Yep. So we reassign current to be equal to what is after current. Current equals current next. And again, using that arrow to dereference it. Head equals current next would move where the start of our list is. So if our head was at a certain node and we said head equals current next, we would move the start of our list to that next node. And normally we don't, well, there are some cases we want to move the head. Right, next up, what would be the while loop condition for traversing all of the nodes in a list? So I've written this while loop condition a few times. When do we want to be moving down the list? Yes, so while current is not null, we will move to the next one. And we'll keep going down the list until eventually current is null, and then we can stop there because we have seen every single node there is to see. Prairie Rooster has the highest answer streak of 6. No, 3 factorial. Right, we're going to run this program. It makes a node, sets a start at a 10. Oh. Right. I'm going to go, is there a way to show the media?
Yeah, press show media underneath the histogram.
That would do it, yeah. The show media button should show the media, you're right. Right, so we start by making a node. So we just make a node that has nothing in it. So this node has nothing in it right now. And then we say that its data is 10. Then we say that it's going to point to a new node which contains nothing in it right now. And so we've got head here. And then we say heads next data. And this is a really cool thing about linked lists that I've been trying to avoid because it can get a bit messy. But you can very feasibly, if you want to, write something like current.next, Python, current arrow next, arrow next, arrow next, arrow data equals current arrow next, arrow data times 12, if you want. And that's a perfectly sane bit of code that you can write. And assuming you have enough nodes, it will work. I don't recommend it, but it can be fun if you just think you're doing too well. Cool. So head next, this is head next, and its data is going to be 20. And then head next, it's next. So head next, next is going to be null. What would be the while loop condition to stop when we get to the last node in the list? Normally we might be inserting something into the list, and so we want to stop just when we're at that last node, because if we go off the end of the list, we can't do that insertion anymore. Yep. So if current next is not null, that means there is something after current for us to look at, and so we want to go there. If current next is null, that means there is nothing after current, and so we want to stop there for some reason. I believe there's one more question. There's two more questions even. Right, oh man. There will be a line in this program that will cause a runtime error. What is it? Oh, I did talk about this. Good job, me. Right. So, there's a split between line 18 and line 19, so let's talk about it. In both scenarios, we're thinking the error will occur because head is null. So let's think about that. So we have null. Head points to it. Is there any reason we can't say current also points there? If head can point to null and the end of our linked list point to null, there's nothing about line 18 that says current can't point here as well. So we're more than happy for current to point here. Do we agree? Are we happy with that? However, what's next? What comes after this? Nothing. Well, it doesn't have an attribute next. So there is no way for me to say what's after null, because that's not a thing. It's not actually a node. It's just null. And so when I try to say what's next, C goes, huh? And then it dies. And so it is line 19 where we ask, while current next, when current is null, is not null. Because what's null next? It doesn't exist, it makes no sense, and therefore C gives up. Cool, we've got one more question, but still so much to quiz for. Right, when should we malloc? It's sort of a bit misleading. I think the question is slightly misleading because technically inserting new data in of itself doesn't require the malloc, but what comes before inserting the new data? Creating the node in the first place, and that requires the malloc. And you can't insert data without creating something, and so you do need to do that malloc to create that node. All right, let's look at the scores. Podium. If you are Awesome Lion, come get a Pokemon card. If you are Focused Bat, come get a Pokemon card. And if you are Smart Dog, what's Smart Dog? Come get a Pokemon card. Are any of these three people physically here today? Well, you'll have to I'm not walking up there. Which one were you? Focused Bat. Good job, Focused Bat. Which Pokemon card do you want? All right, show it to me and the camera. Is it Blipbug? Oh, nice. Big Blipbug fan. Yeah. Were you on the leaderboard as well? All right. Smart Dog, you'll get to choose out of 3.
Oh shit, bro. I don't know what any of these things are. Thank you.
All right, can I see them? I know what they are.
Oh shit.
Nice. Also really nice. Good choices. Sligoo and Apom. Yeah. All right. Should we play again? No. Right. Good job, everyone, though. Right, we're now going to talk about deletion. I'm going to talk for, let's call it 19 minutes, because that's going to take us to 12:50, and then that'll give us some time for questions at the end if we have any, and any stuff that we don't cover can be covered by Sophia tomorrow. Does that sound like a good plan? Cool. Good stuff. Right. We're going to delete in the middle of a linked list. I've pressed the wrong button. I don't want Slack open. Please don't. Oh no. Luckily none of my messages are evil. Right. So we're going to delete from the middle of the list. What's going to get passed in? I've already passed in the head, which is going to tell us where we start. Do I need to pass in a new node when I want to delete something? I'm deleting something, so I don't want to pass in a new node. We could delete by value, so we could delete the node with the first instance of an item we're looking for, but we're going to delete by index instead. So what am I going to pass in here? The index. Actually, before we proceed here, I've realized insert at index has a few errors in it. And these errors arise from the fact that we can't always trust our users to be sensible people. If my linked list is 10 items long, and my user says, please insert a node at index 10,000, my code's going to break. So we need to program for what happens when users do things like that. Furthermore, if they say insert at index -1, well, how is my code going to deal with them doing that? And they need to figure out what are we going to do if the node, if the linked list is empty, we want to insert at a place. We need to figure out how to handle that. And same with if the linked list contains just one item, how we can handle that. I do want to go over deletion, and so what I will say is, please think about these problems. Think about how you would handle if the user inputs an index that's too big, an index that's too small, so for example, negative, and think about what you would do if the linked list just contains the head. So I guess assigned, it's not really homework because I can't force you to do it or anything, but index too large, index too small, only one node in the linked list, and get out a bit of paper and really draw and think about these problems, because that's what's going to make you better at programming and better at linked lists. Right, let's delete at an index now. And the same problems will occur in here. Index too big, index too small, linked list only contains one item, but we're just going to program for the case where those aren't happening. Deletes from a given index. And as always, we're going to introduce our old friend, current. That's going to be the head. And what else are we going to introduce if we're working with an index? Yep, the counter. Set it equal to 0, not 9. And I'll do the same thing as last time. I'll go while counter is less than. Now, if I say I want to delete index 2, where should I stop? If I stop at index 2, it's the same problem as when inserting. 0, 1, 2. If I stop here, all of it, because the change that I want to make to delete index 2 is that I want to take what 1 is pointing at and instead point it to 3. And so actually, again, I want to stop 1 before where we want to do that deletion. So I do while counter is less than index -1. I'm going to go current equals current next, and I'm going to go counter plus plus. This will get us before where we want to delete. And this is a good place to be, because it means we can start thinking about the problem now. So let's say we've got 11. This points to 7. This points to 8. This points to 15. And that can point to null. So our heads here, we're at index 0, 1, 2, 3. And our counter is 0. And so are we going to go to our next node? Yep. So now we end up here. We're at current, which is at index 1. And now what we want to do is we want to figure out how on earth we can remove this 8 from our linked list. And so what are we thinking of here? We need, yeah, so we want 7 to point to 15. And because there's no way to go backwards, we can't access 8 anymore, which is fine, but this will cause a problem when I free all of my nodes. Because what's going to happen when I go through my list and I go, I've freed 11, I've freed 7, I've freed 15, what's going to be sitting there taunting me? Unfreed, 8. He'll be there, ready to cause problems if we give him the chance. And so what we have to do when we are deleting our nodes is make sure that we free the node that we delete. Because if we don't free it, then it's going to get missed in our last call at the end, which goes through our list and frees all of our nodes because he's no longer part of our list. Are people happy with that idea?
Yeah.
Cool, nice. I love lectures in a way because one person saying yes, I'm just like, oh, that must mean everyone agrees. Right, so how will we do this? Let's start with making a node pointer, and it'll be called node to free. What node do we want to free? Yep, current's next, because we're at current, and we'll eventually at some point want to free current next. Now, here's the part where you can start writing some pretty crazy linked list stuff, and I'm going to do it. So now, what do we want current next to equal? Current next should equal current next next. So current next equals current next next. So we're at current. And current next points to that node we're going to free. So we're going to free this at some point, but it currently points here. We want it to not point there. We want it to point at what comes after, or the next next, which means current's next right now, this pointer, is no longer going to point here, but it's going to point down here. Now, that's the way that I enjoy to write it. The probably nicer way is doing something like struct node star to point at is equal to current next next, and then current next will be what we want to point at. And again, we'll just return head at the end. Oh, what have I forgotten to do? What was that whole thing that I gave a mini lecture about? I didn't free it, so I should free it. When should I free it?
After you point it 7 to next, yeah?
Yeah. What would happen if I free it here?
You will lose it.
I'll lose it, and I still need it right now. And so generally I find it safest to free just right before I return, because then I know I don't need it anywhere else. So I'm going to free node to free. But first, before I do that, I'm going to comment it out, and we're going to run it with the leak check and see if we get that error. So let me clear my terminal. Let's run. I've not deleted anything yet. Yep, our linked list is here, 11, 8, 55. So now, let's go head equals, what do I call the function? Delete from middle. It should be delete at index because it doesn't necessarily have to be the middle. We're going to delete at the index. We'll pass in the head, and I'm going to delete at index 3. And now I'm going to print the linked list again with the head, and hopefully whatever's at index 3 will be gone. Oh no, what have I done? Oh, right, yeah. Okay, that's fine. Yep, thank you. He's so picky. Right, so it has removed the item from index 3, but free has not been called on a bit of memory that we've mallocked. And now, once I uncomment this bit here, now our memory's been freed, and we're all happy, and we're all healthy. Are there any questions about deletion? I'm going to go through and comment the code real quick, but please shout out some questions at me.
Would it be more better style if you did the current, instead of current next, you do a node to free next?
Yeah, probably. Yeah. It's personal preference. I like dealing with current, but I think it's personal preference. Is there something in the style guide about it? Do we care? How many next they string together?
It's just more about if current next is equal to null.
Yep.
Stop doing null next, which is a really bad habit. So we do encourage you to not do like 2 in a row, because you should be checking for nulls first before you do 2 in a row.
That's true. But, okay, so for people on stream, we encourage you not to do 2 in a row because you need to be absolutely certain that one of those next isn't going to encounter a null. And so it's really bad practice to do multiple in a row like I've done here. But when you do it, you feel this overwhelming sense of power. And so it is like swings and roundabouts. But no, you probably shouldn't do it. I'm a trained professional. I do dangerous stuff like this all the time. Right, we've got about 5 minutes. I'll comment this code, and then we'll talk about some of the pitfalls. Hello.
There's a question on one that says if index is equal to 0,
Yep.
we need to do something else.
Yes, that's one of the pitfalls. If index is 0, we will need to do something else. Good question. We want to go. Guess the node we want to delete. Guess the node we want to point at next. And so what they were talking about here is that what I should really do in this scenario is I should check, I should go if, something like if node to free next does not equal null, which ensures that I'm not doing a next with a null. Then I'll change this to be node to free next. And if node to free's next is null, what should I point to later? I'm going to say that I'm going to point at, this what? I will just do this for now. Hey, quick question, can I do this? I've not come across it before. Is that allowed? All right, cool, nice. So if, oh man, you're gonna be loving those caramello koalas. Have you gotten any? Yeah, good, good. Throw it at them again, no. So this is just checking that we're not accidentally doing.
Also be on the ending bracket for style, right?
Stylistically, probably, I've not read the style guide. The fact that I've managed to make it this far into the lecture without getting caught out by the style guide, I see that as an absolute win. Right. So this is the sort of stuff you need to be thinking about. What if you're doing next and one of them is a null? What if the head is a null? What if the index is too large? What if it's too small? I guess the node we want to free. Only if it exists. Otherwise, we will point to null. So someone online asked about what if index is 0, and actually let's find out what happens if index is 0. And if we don't have enough time to get through all of it, then that's okay. We've got about 3 minutes, so we probably won't, but let's see. Oh no. On line 127.
Oh, you needed to declare the mirror on the side.
Sorry, what?
Like, declare the struct node to point out outside of the...
Oh man, I didn't, okay. Fair enough. And then I can get rid of these. I think part of the appeal of live coding is that it shows you that even though I've been programming for a decade at this point, I still make mistakes. Programming is about fixing your mistakes. And occasionally it's about peer programming and getting others to help you. Cool. So this is our delete at index function. Let's see what happens if we put index 0. Oh, it worked. No, it didn't work. Did I save it? Yeah, it's deleted the 8, which is not at index 0. 8 is at index 1. However, I have got 0 minutes to explain that. And so if we... Was that a hand? I've got 5 minutes. Oh, okay, I'm used to going to 10-2. All right, I got 5 minutes to explain it then. Let's walk through what happens if index is 0. All right, so first I say we've got current equal head, counter is 0. So counter is 0. What's index minus 1? Negative 1. Is 0 less than index minus 1? No. 0 is bigger than negative 1. So what? Yeah, how does 8 get deleted here? The node to free. There's some wild stuff happening here. I should be able to figure this out. Oh, I'm floundering. All right. Well, let's write the special case anyway. Let's check if the index is equal to 0. That means you want to delete the head. If the index is 0, you want to delete the head. And so what we'll do is we will say, head next. no, sorry, we're going to say head is I'll go struct node star, the previous head will be equal to what our head currently is. This is what head used to be. Now I'm going to say head equals head next. I'm going to free the previous head, and I'm going to return what the new head is. And if I do that, I'm hoping, yeah, now it's deleting the one at the front. You should also think about why it was not deleting the one at the front before. Walk through it on a bit of paper, on a whiteboard. You will get paper in the exam. I highly, highly recommend you use it for linked lists. Right.
Can you try to one, please?
Can I try one?
Yeah.
Yep. So let's clear this, and I'll try it with one now. Yep, and it deletes the one at index 1.
Why was deleting 8 before when you did develop this error check?
Yeah. So the default behavior is stopping at, I just realized it now. The default behavior for this while loop is stopping when we are at 0, and then it points 0 to the 1, it points 0 to 2. So I'll see if I can get this really quickly. So what was happening before that I couldn't comprehend now, but I can now, is that this was our current, and we were saying current points here, but we want current to point here, which meant that even though our index was 0, because our while loop condition was probably not the best we could have made it, we then set currents next to be currents next, which got rid of 1. It's a bit of a confusing one. I recommend playing around with the code a bit, but the point is that it is the behavior we expect because our while loop condition was not the optimal while loop condition, or sometimes just need to deal with special cases in linked lists. All right. It's now 12:55. Thank you very much for coming to my very first lecture at UNSW. My goal is that after these next few weeks, when Jake comes back, you're all really sad about it. And so if you could give some feedback just about the course in general, about how we're doing, whether you want me to teach the course in future years, all that fun stuff. Thank you very much. I'll stick around and answer some questions. Sweet.